Today we're going to look at electric current. So you've probably talked about electric current, but today you'll be able to figure out exactly what it means. So let's think about an analogy first. So imagine two rivers and think about the current in these rivers. So here we have the Mississippi on the left, and Mississippi flows fairly slowly most times. The velocity is about zero point 0.3 meters per second, so I'm not going too fast. On the other hand, you have the Pigeon River, which flows through Gatlinburg and Pigeon Forge, and it's a fairly fast moving river. It moves about 3 meters per second. So, which river do you think has a greater current? And what does that tell us about the word current and what it means? So I think most of you would probably say that even though the Pigeon River is going faster, the Mississippi has more current. So clearly current isn't just about how fast it's going. When we talk about river currents, it's not just about how fast the water's going, it's about how much water passes a given point in a certain amount of time. So in a typical average, the Mississippi, about 600,000 cubic feet of water pass any given point in a second. So if you were to sit there in St. Louis near the arch looking at the Mississippi River, in 1 second, 600,000 cubic feet of water would go by. On the other hand, the Pigeon River, although it's moving faster, has a much smaller amount of water going by every second. So only 1,000 cubic feet of water go by every second in the Pigeon River. So we would say the Mississippi River has a greater current. So when we talk about current, what we're actually discussing is the volume of material that goes by in a given amount of time. For rivers, that's cubic feet of water per second. For electrical current, when we talk about current, we mean how much charge flows by in a given amount of time. So the stuff we're interested in is charge, and electrical current will be how much charge goes through a conductor in a given unit of time. We're going to measure electrical current at a unit called an amp or an ampere. And 1 amp means that 1 coulomb of charge goes by in 1 second. So if you were to sit and stare at a wire and 1 coulomb of charge were to go by during 1 second of time, we would say that the current is 1 amp or 1 ampere. So calculating the current is pretty easy. Now we use a goofy variable for current. We use capital I. Our mathematician friends are having fits because I is a reserved letter and generally not used. We're using the uppercase version because in physics we use the lowercase I as the imaginary number. But the mathematicians notwithstanding, we're going to use capital I for current. We can't use C because that's something called capacitance. And so we're going to use I. So the current that flows is the charge divided by the time. When the charge is measured in amperes and the time is measured in seconds, 1 amp per second, 1 coulomb, when the charge is measured in coulombs, 1 coulomb per second is what we call an amp. So when you write this down in your toolbox, it might be helpful to just note the amp is actually a coulomb per second, and that's going to help you probably when you solve some problems. So if you were to imagine a conductor, so we're looking at a cross section of a wire here. So we have some little area here, A, that we're inspecting. And if we figure out how much charge Q passes that little area in a given amount of time, 1 second, then we have found the current. All right. So a typical appliance, a stove might draw 30 or 40 amps when a couple of burners are on. That means it's 30 or 40 coulombs of charge is flowing through your stove in 1 second. Okay, that's what an amp is, or an ampere. Now, what direction is the current flowing? Well, Ben Franklin figured out there were two kinds of charges, positives and negatives, and he thought the positive charges moved. And so he defined the conventional current flow as the direction that positive currents would move. So if you imagine a battery right here, and this is the positive side of the battery, the positive charges will come out and go around the circuit. So the direction shown in red is what we call the conventional current flow. It's the direction that the positive charges would flow if Ben Franklin had been right. But it turns out he was wrong. The positive charges don't flow. The positive charges are anchored in the nucleus, and the nucleus of, for example, a copper wire does not move. It's the electrons that move. And so We sometimes talk about the electron flow, which is the direction that the actual negative charges go. So it gets a little confusing. We're not going to try to trick you or anything here, but just keep in mind that there's two different directions. One is called the conventional current, and that's the direction positive charges would flow if they flowed. But in actuality, electrons flow and they go in what we call the electron direction. Okay? All right, so let's just do two example problems before we turn you loose to solve some problems on your own. I've got a hairdryer and I want to know what is the current in the wire if 1,000 coulombs of charge go by in 1 minute. Okay, so 1,000 coulombs of charge is the amount of charge, Q, that's going to go by, and the time is 1 minute. Okay, so you just got to be a little bit careful because we are working with amps, and amps is coulombs per second. We got to do a conversion here. 1 minute is 60 seconds. So what we really have is 1,000 coulombs of charge going by in 60 seconds. So to find the current, we just take the ratio of the charge to the time. So that is 1,000 coulombs divided by 60 seconds, or 16.7 amps. So this hairdryer would require a flow of 16.7 amps in order to operate. That's how much the flow there is going to the hairdryer. Another example involving your phone. Let's suppose you connect your iPhone to a charger that delivers current at 1.25 amps, or 1.25 coulombs every second. Okay? So if we have that much current flowing, and it takes a full hour to charge the battery, how much charge was transferred? So in this case, we know the current is 1.25 amps. We don't know how much charge there is, and we know the time is 1 hour, which is 3,600 seconds. And we're actually not going to use the voltage yet. We're going to use that down below when it asks how much energy. So what we're going to do is we're going to solve I equals Q over T for Q. We know the current. We know the time. We want to know how much charge is transferred to your iPhone. So to do that, we simply solve this for Q. So Q is equal to I times T. Take the current, 1.25 amps. Now remember, amps is coulombs per second. So if you have 1.25 coulombs every second times 3,600 seconds, you get 4,500 coulombs of charge. So it takes 4,500 coulombs of charge to completely charge up your iPhone battery. All right. A second question to ask with that is how much energy was stored. So back in the last lesson, we learned that the voltage is the energy divided by charge. And so if we know the voltage, it's 5 volts. That's what those little bricks you have with your phones are. And we know the charge, Q, we just found that here in part A, we can find the energy that is stored in your battery. And so the energy will be the voltage times the charge. So 5 times 4,500 is 22.5 kilojoules of energy is stored in your phone when it is fully charged. Okay? So the big idea is here I equals Q over T. We're just going to solve problems with this. Keep in mind that I is the current. It's measured in amps, which is a coulomb per second. So if your charge is not in coulombs, you got to get it in coulombs. If your time is not in seconds, you got to get it in seconds in order to use amps or amperes. Okay? Alrighty. So time for you to solve some problems. Homework 9.3 has got a problem set, and we're just waiting for you. You can thank us later.